This is gonna be the last revision video we're gonna upload before your mock exam. It's regarding the first unit, Unit 1. I will do a quick, very quick summary of the formulas, units, stuff like that that are included in Unit 1 and then the stuff that you should know 100%. And then I chose a question to do with each chapter and we're gonna solve them quickly. Let's start up without wasting any time. Unit 1 starts with the first chapter talking about the laws of motion. Okay, it's built around an idea that tells you that average speed equals distance traveled divided by time taken, which is something we always refer to in another way by saying speed or velocity v equals distance, which we refer to as the letter s, divided by the time. Okay, one thing that we need to make sure that you guys understand 100% is the units for speed that we use are usually meters per second or kilometer per hour. For distance we use meters or kilometers, and for time we always use seconds or hours. Okay, then it gives you another concept called acceleration, and we defined acceleration to be a change in speed, either an increase or a decrease in speed. And the formula for it, we said that acceleration is basically final speed minus initial speed divided by time. Because I told you it's a change in speed, you're supposed to have two speeds, a final one and an initial one. Both speeds measured with meters per second in this case, time in seconds, and acceleration ends up having the unit of meter per second squared. Okay, after that we take another formula that can also calculate final initial speeds and acceleration for us if the question doesn't mention time and it mentions distances instead. The formula is v squared, let's write them all in blue, v squared equals u squared plus 2 multiplied by acceleration multiplied by the distance. All right, when do you use this formula? If instantly it's a question about calculating speeds or acceleration, but you don't get time given to you in the question, instead it gives you distance, then you can't use the formulas up here, this one or this one, because both of them have time and the question might not give you time. If it gives you distance, you instantly need to use this formula instead of the normal acceleration formula. All right, obviously the units are the same, meters per second for this one, meters per second for this one, acceleration is meters per second squared, and distance is meters. Okay, now usually we deal with solving such questions, but we deal with them inside graphs. We have two types of graphs, if you remember with me, that you need to revise. Okay, the types of graphs that you need to revise are the velocity time graph and the distance time graphs. This one is more likely to be asked about than this one, even though they ask about this one. I don't want you to, make it a standard that it's always a velocity time graph, but there are more velocity time graphs than there are distance time graphs in past papers. Okay, and you're supposed to know how to calculate stuff inside a velocity time graph and inside a distance time graph. For velocity time graphs quickly, so velocity time graph, you need to understand a few things. Okay, and the stuff that you need to understand here when it comes to velocity time graphs is that it might ask you to calculate, first of all, the acceleration. It might ask you to calculate the distance traveled, or that those are the two calculations, or other than that it might ask you for velocity or time and you need to get them through the graph. Now what I want you to memorize here, please, if it ever asks you to calculate the distance, always check the area under the graph, and the area under the graph is gonna be like a shape, either a square or triangle or a rectangle, something like that that you can actually deal with and calculate. Acceleration, you just go to the formula, which is v minus u divided by t, and take your values from the graph, which is no issue. Distance time graph is easier. You just basically, you will know how to deal with it like we did it practice in class. It's not something that I'm worried about you guys messing up or anything, right? Okay, after you finish chapter 1, it starts talking about forces. The main thing that you should never forget about forces is that the main formula for force is force equals mass multiplied by acceleration, plus other stuff that you should know, such as Newton's laws. Sometimes I see some questions where it asks you to, for example, state Newton's second law or state Newton's third law. You'll find them in your book in some sections. You need to memorize them, not line by, actually try to memorize them line by line, but at least you need to know what's the law and what does it state and what does it mean. Okay? And then studying wise, you should move on to the end of chapter 2. You will find at the end of chapter 2 something to do with springs. And I'm talking specifically about Hooke's law. You need to understand what's Hooke's law and you need to understand what does it state. Hooke's law just tells you that there is a direct proportion whenever you're dealing with a spring or wire, those shapes. Okay, it just says that the more force or load that you apply on the spring or the wire, the more it will extend. Okay, it's very explanatory from what I said, meaning if you have a spring or a wire, if you pull on it strongly, the harder you pull, the more it will extend, becoming longer. But this needs to happen in a direct proportion. Okay? If you take a look at the graph of Hooke's law, you'll always see it looking like this. One side is going to be the load. The other side is going to be the extension. And you will see the graph being a straight line. Okay, so it needs to be a straight line and it needs to start from the 0, 0 point because it's a direct proportion. Okay, any other shape that you might see that's not like this is not a Hooke's law. Okay, and by the end of it, after extending for some time, you will find that there is always a breaking point at the end. Sometimes it looks like this, sometimes it looks like it's aiming down. But this breaking point is something we call the limit of proportionality. Okay, and it happens because if you pull a spring, think about it realistically. If suddenly you start, sorry, in this case it would pull downwards. Okay, if suddenly you're pulling on a wire, a spring, whatever it is, anything that literally expands, if you pull on it too strongly, eventually you will reach a point where the thing will reach a maximum length. Like imagine this spring right here, the one that I drew. If you pull on it too strongly, it will eventually become something like this. And if you keep pulling more, it will get cut or it will break. Even this point right here, it has reached a limit where once you let go of your hand right here, it will not go back to the original shape. It can't do that anymore. Why? Because you've pulled it too strongly. Alright, and that's what Hooke's law basically states. It says, as long as you're dealing with a spring and wire, the more you pull, the more it should extend in a direct proportion. And then eventually at this point, it will reach a place where it will no longer be able to go back to the original shape if you stop pulling. And if you pull any further, it will completely cut the wire. Alright, once you finish all of these, you've pretty much finished chapter 1, 2, and 3 by, as I told you, studying the motion laws, studying velocity time graphs and distance time graphs, and then Newton's formula, Newton's laws, and then you go and study Hooke's law and how does it operate. That's it. You finished chapters 1 and 2 and 3. That leaves 2 chapters for you to study. Okay, now I have the page on the top here. The chapters that are left are momentum and moment. Okay, let's start with momentum first of all. Momentum basically explains to you how difficult it is to stop an object while it's already moving. And the formula for momentum, the letter we use for it is P. It tells you it's mass multiplied by velocity, meaning if something is heavy or if it's moving too fast, it's going to be way too difficult for you to stop it. The formulas that you should know is this one, first of all. Okay, the unit for momentum, look, mass, the unit for it is kilograms. Velocity, the unit for it is meters per second. So the unit for momentum is kilogram meter per second. Okay. Now, other formulas that you face in momentum, because as we know, there are multiple formulas inside momentum. There is this one, and there is another one connecting momentums with forces. It says force equals final momentum minus initial momentum divided by time. You might see this line referred to as change in momentum or increase in momentum. Okay, and if it ever asks you in the question to calculate the change in momentum or increase in momentum, please understand that change in momentum equals, you rearranging the formula right here, change in momentum would be this multiplied by this, because they're a divide, you take time to the other side, it will become a multiply. Okay, so it would equal force multiplied by time. Okay, and lastly, there is a principle of momentums, the one that tells you in collision, sorry, not a principle. There is momentums in collision, and you need to understand that momentums in collision, the principle says that momentums before collision have to equal momentums after the collision. So you need to check how many, basically if you're talking before the collision, then you definitely have multiple objects. Take the mass of the first object multiplied by its speed plus the mass of the second object multiplied by its initial speed equals on the other side. Their masses are gonna be combined in case the objects stick together. Okay, and if the objects do not stick together, then again treat them separately. The mass of the first object multiplied by its new speed after a collision plus the mass of the second object multiplied by its new speed after the collision. Those questions, the formula right here is changeable depending on the question. Sometimes the initial speed is 0 of one of them, so you'd remove it as 0. Sometimes the final speed of one of them is 0, you'd remove it as 0. Sometimes both objects stick together, so instead of doing M1 and M2, you would replace them with another thing called M1 plus M2, because now they're stuck together. So you just need to analyze it depending on the scenario, which is the difficult part about this chapter. Okay, but you need to know the principle that always the momentums before the collision are equal to the momentums after the collision. All right, that leaves one thing that you need to study, which is moment. It's simpler than momentum. Moment is just a turning effect. Okay, so in order for you, if you want to turn something or spin it around clockwise or anti-clockwise, you can multiply the amount of force that you're doing by making it a big distance between you and the thing that you're trying to spin around. That ends up giving us a formula that says moment equals force multiplied by distance. Okay, we measure our forces in Newton, we measure our distances in meter, giving us a unit for moment being Newton meter. Okay, moment also has a principle when there is some stuff that we call balanced or an equilibrium. And in balanced moments, we know that moments clockwise equal moments counter or anti-clockwise. And we will see that in the example I displayed. Now, that concludes everything you need to know as basis information for both momentum, moment, movement, forces, and Hooke's law. Now, I added a question about almost each one of them down here, and we're gonna go solve them quickly because I don't want to make this video a long one. First of all, we're gonna start with a graph. It's a distance. It's a very weird graph that I found, and I think it's important for us to understand it. But we're basically doing the first chapter of movement using this graph. The graph has distance, but instead of time, it has speed. Okay, so it's a distance time graph, something that we haven't, distance speed graph, something we haven't actually solved before, because it's a special case that I've only seen in this question specifically. But because we've dealt with enough graphs, we shouldn't have an issue solving it. You'll see that it's very simple to deal with. The graph shows how thinking distance and braking distance vary with the speed of the car. This is a part of chapter 3. Okay, the thinking distance and the braking distance, and we will cover it within this question, inshallah. Okay. Look here. Which of these does not affect thinking distance? Now, remember with me, before I answer both of these questions, in order for a car to stop, or for a vehicle to stop, okay, it's separated into two sections. A thinking section, sometimes referred to as the reaction section, okay, plus the actual braking section. Okay, what do I mean by this? I mean, whenever there is a vehicle that's intending to stop, the driver takes some time and some distance crossed to make the reaction. And by that, I'm talking about when they see the obstacle, by the time their foot reaches the braking pedal, all of that. it takes some time and some distance in order for you to make this reaction. Plus, after that, once you hit the brakes, the car will take some time to stop. So the entire stop is separated into two sections: a reaction and when you hit the brakes and wait for the car to completely stop. This all is called stopping distance, referred to as thinking distance plus braking distance. Now, it's always separated into two sections. The thinking is always about the driver, because he's the one making the reaction. Him having fast reactions or not, being sleepy or not, being under the influence of alcohol or not, being tired or not, all of those affect the driver, so we all put them with the thinking part. The braking is all about the car, or the vehicle in this case. Let's say vehicle because sometimes it's not a car. Okay? Why is that? Because you hit the brakes. You as a driver, you've done your work. You've already hit the braking pedal, and now you're waiting for the car to stop. If your car has bad brakes, it will take longer. If the road was slippery, which would affect your car again or your vehicle, it will also take longer. Okay, if your tires are not new, that would take longer. So we separate it into two sections, one that affects the driver and one that affects the vehicle itself. All right? Now, let's start analyzing the situation right here. Okay, now to answer such questions, we just need to worry about it. Are we talking about thinking or braking or stopping, which is the total between both of them? And when we answer the questions, we just need to analyze it properly, that when it's talking about thinking distance, we need to worry about the driver. When it's talking about braking, we need to worry about the vehicle itself. So let's look at the first one. Which of these does not affect thinking distance? So think about something that does not affect the driver. All right. Alcohol consumption by the driver. This affects the driver, so it can't be this answer. Conditions of the road. This doesn't affect the driver. Speed of the car. Speed, again, I want to mention that speed of the car is the only thing that affects both thinking and... because if you're driving fast as a driver, it makes you drive too much for you to make the reaction, if that makes sense. Tiredness of the driver. So all of these, A, C, and D, they affect the driver. The only one that doesn't is B. So this is the right answer. Okay. Moving on. Which of these would increase the braking distance of the car? Which would mean that it takes you a longer time to stop the car, and it takes you a big distance for you to stop the car. A faster reaction time of the driver. No, this would make you stop quickly, and it has no effect also about the braking, because it's something to do with the driver. It has nothing to do with the braking, so it's not the right answer. Okay. Ice on the road. Ice on the road would make you take a long time to stop, so it would increase the braking distance. More powerful brakes would make the braking distance shorter. It would make you stop quickly, and here it's saying increase the braking distance, meaning it takes you a long time to stop. Tires with more grip, again, it would make it a quick stop. So the answer is B. Okay. Determine the stopping distance of the car when the speed of the car is 20 meters per second. So it wants the stopping distance. And remember with me, the stopping distance, guys, is both the thinking distance plus the braking distance. Okay, look at the graph. Oh, sorry. The important piece of information is that we are talking about when the speed of the car is 20 meters per second. Scroll up here. The speed is 20. Okay, and right here on the other side we have the distance. So let's take, first of all, we have two lines. We have a thinking distance line, and we also have a braking distance curve. Sorry, not line. Okay, so first of all, we need to go that when the speed is 20, and we need to make a dotted line until we reach the thinking distance. All right, now we're trying to figure out the distance, so we're gonna make a straight line to the left all the way until we reach this. So the thinking distance the driver drove was 10 meters, but the question asks us to calculate the total stopping distance, which means it's the thinking plus the braking. Now we got the thinking to be 10 meters, no issue, plus the braking. Let's check the braking. This is the line for braking. Again, we're talking about when the speed was 20, so we're going to continue our dotted line upwards until we reach this point. And once we reach this point, we're going to take a left, which would give us right here 26 meters. Okay, so plus 26 meters, which adds up to a total of 10 plus 26, which is 36 meters. I hope that's no issue, okay? Moving on to the question afterwards. State the formula linking average speed, distance moved, and time taken. We already know that average speed equals distance moved divided by time taken. The same formula, right, as speed equals distance over time. I just wrote it with full letters. Determine the reaction time of the driver. Remember with me, reaction is a word to refer to thinking. Okay, so we need to basically figure out the thinking time. Rearrange the formula. Time equals speed divided by distance. Okay, if you do it in a triangle like this, you would end up with distance on top, speed, and time. If I'm trying to calculate the time, it's distance divided, distance divided by speed, which means I got it right here wrong. Hold on. Time equals distance divided by speed. All right, so we need to go to the graph and figure out the distance, figure out the time, and just divide them together. All right, so let's go up there all the way here. Look at the thinking distance graph. Let's erase these because they're confusing. Okay, and let's take a good look at the graph. We're gonna worry about the thinking distance. Okay, his speed when he started braking was 30. Okay, and the amount of distance that he traveled was 15 meters. So in order for us to figure out the reaction time, we just take the speed of 30 meters per second and we take the distance of 15 meters and we go to the formula straight up. The formula says that time equals distance divided by his speed. His distance was 15, his speed was 30, so his reaction time was half a second. Okay, now why did I take the numbers from the end of the graph? You might ask yourself. Look, it's a braking scenario where the driver slows down the car. The highest speed he reached was 30, therefore when he starts to brake, it should go back to the speed of 0. Okay, so he stopped his car from being 30 meters per second, hit the brakes until his car reached 0. So I need to take the maximum speed he was at and how much distance did he travel in order for him to reach the 0 point. Okay, so all you need to do is just rearrange the formula real quick. Speed equals distance over time, as we know. We changed it into time equals distance over speed, and then we calculated and it was half a second. Last question, calculate the mean braking acceleration. So this time we need to go look at the brakes, not at the thinking, of the car as it brakes to a stop from an initial speed of 30 meters per second. So we have the initial speed being 30 meters per second, as mentioned right here. It says that it brakes to a stop, meaning that the final speed is going to be 0 meters per second. Okay, and he wants us to calculate the acceleration. No, calculate the mean braking acceleration. Yes, he wants us to calculate the acceleration. All right, now do we have time here? That's the question that we should be asking yourselves, and we don't have the time here. Therefore, we are forced to work with the other formula, okay, because it didn't give us time right here. Why? Because if you go to the graph up there, you can figure out the distance, and if you can figure out the distance, then you can just like start using it. It says calculate the mean braking. So you go all the way up to the graph, okay, and you need to look at the line that says braking distance. What's the maximum distance it reached? Right here, it's 54 meters. Okay, it broke the distance of 54 meters, sorry, from this speed that's very high all the way until the speed reached 0. Okay, so take your distance as 54 and go to the other formula because you're forced to use it. The other formula, let me just make more space for myself here. V equals 0 and the distance is 54 meters. The other formula states V squared equals U squared plus 2AS. And let's start working with it. Okay, the final speed is 0. The initial speed is 30, but don't forget the square, plus 2 multiplied by the acceleration, which I don't know and I'm trying to calculate, multiplied by the distance, which is 54. Okay, now let's simplify it. 0 equals 30 squared, which is 900. Let's double check. Yes, 900 plus 2 multiplied by 54, which should give you 108. Okay, 2 times 54, which is 108, multiplied by acceleration. Now we have a plus between them. We can take one of them to the other side. Okay, this is what we're gonna do. It becomes 108 acceleration equals on the other side negative 900, because the 900 was positive right here. When you take it to the other side, it becomes negative. Divide both sides by 108, and your acceleration at the end should be 900 divided by 108, except for that the 900 is negative. So your final answer would be negative 8.33 meters per second squared. It's a tough question. It's worth 4 marks, but that's the final answer to it. Rewatch it again if you don't understand it first time, or listen to me as I repeat it again. It told you that the initial speed was 30. It comes to rest. Okay, it breaks to a stop, sorry, so the final speed is 0. The only issue that you need to calculate the acceleration is you need to find out the distance. Go all the way to the graph. Look at the line that says braking distance, and braking means that you were at a high speed and you had to go to a stop. So check the highest point, take the distance from there, and use this highest point when you take the distance all the way down there to calculate it right here in the formula that we just used. This is a difficult question I found regarding the first chapter, and yeah, it covers a lot of different topics in one question. Okay, now let's move on to a question to do with, let's leave this one for later. I want to move on to a question to do with forces, which is this one. A photographer, we already know this question, we've dealt with it before, but let's resolve it. A photographer shows a whale jumping out of the surface of the sea. At the top of the jump, the whale's velocity is 0 meters per second. The whale falls 2.2 meters from the top of the jump onto the surface of the sea. Calculate the velocity of the whale when it hits the surface. Again, another question. It wants you to calculate velocity, and it gives you distances, which means you need to use the other formula. The formula says v squared equals u squared plus 2as. The trick in the question is that in any free fall, when an object is falling down, acceleration is always equal to gravity, which is 10. Okay, don't forget about that, please. And now in any future exams, there is a reason I put it in a question back in the days, because I don't want you guys to forget about it at all. So let's solve it. It said calculate the velocity of the whale. So I'm gonna leave v as missing, equals, what's the initial speed? 0 plus 2 multiplied by the acceleration, which is 10. Don't forget about this, please, because he's falling down, and the only thing for pulling the whale down, it's falling down, and the only thing pulling it down is acceleration as the gravity, and the gravity is always 10 on Earth, so don't forget about that. Multiply by the distance given to me is 2.2. Okay, multiply those three together. V squared equals 2 times 10, which is 20, times 2.2, which is 44, plus 0, it stays as 44. Take the square root to both sides, and the final answer is 6.63. Okay. B. A resultant force causes the whale to slow down when it hits the surface of the sea. Draw the arrow to show there is this resultant force. Remember with me, he's falling down. So since the resultant, it's falling down, sorry. Since the resultant force causes the whale to slow down, that means it needs to be in the opposite direction that it is moving in. So it needs to be upwards. That's, or to make it more accurate, in this direction. Because if we drew the resultant force downwards, that means it's making it speed up faster, you know. And it said when the whale hits the surface of the sea, so the whale was going down, something slowed him down. So since it's something that slows it, it needs to be in the opposite direction of the whale's movement. The resultant force acting on the whale is 1,800 newtons. The mass of the whale is 4,100 kilograms. Calculate the acceleration of the whale. We all know that force equals mass multiplied by acceleration. He wants us to calculate the acceleration, so the acceleration would be force divided by mass. The force is 18,000. The mass is 4,100. Just divide those two together quickly. Okay. .39 meters per second squared. Okay. Is that it? No, it's not. The other questions are up. Now a question to do with the moment real quick. It says a pencil has the weight of 0.16 newtons. What's the mass of the pencil? Okay, we just need to figure it out very quickly. So we all understand that weight is mass times gravity. If I'm trying to find out the mass, it's mass equals weight divided by gravity. So the weight is 0.16, gravity is 10. Divide both of these together, it's going to give you 0.016. All the answers right here are given in grams, not kilograms, because this answer that we got right here is kilograms. We need to change that into grams. So you take 0.016 multiplied by 1,000. Okay, and it would give you, if you move the decimal few steps, 16 grams, which is this one. Okay. Moving on to the second point, the diagram shows a pencil with one end resting on a small block. Okay. A finger point provides an upwards force F to keep the pencil horizontal. This is the upwards force F. The weight of the pencil is 0.16 newtons. Okay. Calculate the moment of the weight of the pencil from the pivot. Use the formula this. Okay. So this is the weight of the pencil, 0.16. How far is it away from the pivot? It's 3.7 centimeters, and it just wants us to calculate its moment. Remember with me, moment equals force multiplied by perpendicular distance from the pivot. The force of the weight is 0.16. Multiplied by perpendicular distance, which is 3.6 centimeters. Change that to meters. Divided by 1,000. It becomes 0.0037 meters. Oh, sorry. You need to divide by 100, not 1,000. My bad. So it becomes 0.037 meters. Okay. You just need to multiply those two numbers together. 0.16 multiplied by 0.037. Okay. Gives you 5.92. Oh, my bad. I am very sorry because I solved this question very quickly. There is no need for you to change the unit into meters, because if you look at the answer, it gave it to you as Newton centimeter. So just take the distance the same way it is and centimeters, and don't convert it. Okay, it's good I made the mistake so you guys can see it, because it wants you to solve it in Newton centimeters. So take the force, which is 0.16, multiply it by 3.7 without converting, without doing anything, which makes it easier, you know. Final answer 0.592. Moving on. State the moment of the force F, and the moment of it needs to be 0.592. Why? Because we said moments clockwise need to be equal to the moments anti-clockwise. And remember with me, the finger provides an upward force to keep the pencil horizontal. It's balanced. This entire shape is balanced right here. So whatever moment is being created by the weight, the guy is countering it with his finger. The moment created by the weight, we calculated it as this. So the moment by the finger will also be the exact same value. Show that the force F is 0.080 newtons. We just need to use the principle of moments, which says moments clockwise. Okay, moments clockwise equal moments counterclockwise or anti-clockwise. Okay, let's start with the moments clockwise, which are this finger right here. The force of it is F. And how far is it away from the pivot? It's 7.4 centimeters. So let's take F multiplied by 7.4. That's clockwise. Equals on the other side, counterclockwise. We have the force of the weight. The value of it is 0.16. And it's 3.7 centimeters away. So all we need to do is 0.16 multiplied by 3.7. That's it. It's simple algebra. We can use it to calculate. Those two multiplied together gave us earlier when we did them 0.592 equals on the other side 7.4 F. I'm trying to find out the value of F, so I need to take this to the other side as division. F equals 0.592 divided by 7.4. Okay, 0.592 divided by 7.4. The right answer that we're gonna get is 0.08 newtons. which is the exact same number he said right here. Last question, it's going to be regarding momentum. It says cricket is a sport played with bats and balls. A cricket player hits a ball with a bat. Before the ball hits it, before the ball is hit, it is moving to the left with a momentum of 3.9. So before he hits it, the ball was going this way with a momentum of 3.9 kilograms meters per second. The bat is contact with the ball for this time. So this is the time given to us right here, 0.005 seconds. After the ball is hit, it moves to the right with the momentum of 3.8 kilograms meters per second. So after that, it changes direction to the right. The momentum is 3.8 kilograms meter per second. Calculate the mean force that the bat exerts on the ball and state the direction of it. Since it's asking us to do force and it's a question about momentums, we're going to have to use the formula of momentums. The formula says that the force equals mv minus mu divided by time. Mu is the momentum of the ball before it was hit, because it's the initial momentum. Mv is the momentum of the ball after it was hit, and the time is given to us as 0.05 seconds. Therefore, the force is going to equal to us mv, which is the momentum of the ball afterwards, and we're going to do it as 3.8. Okay. Minus from the formula, and another minus which I will explain right now where I put it. The momentum at first, which was 3.2, divided by the time, which is 0.005 seconds. Okay, do that in the calculator. Those two minuses are gonna be positive because minus and minus give you plus. So actually it becomes force equals 3.8 plus 3.2 divided by 0.05. Okay. Which gives you a force of 140. Okay, and the direction of it is since the calculate the mean force that the bat exerts on the ball and set the direction of the force, it's going to be to the right because that's the direction the ball was being hit at. State the magnitude and the direction of the force that the ball exerts on the bat. It's going to be the exact same value, but it's going to be to the left. Now let's explain why I did everything that I did right here. Okay, first of all, I want you to look at this. The ball is moving to the left and the bat is moving to the right, meaning that they are moving in opposite directions. Okay, whenever there are two things that you're calculating and they are in the opposite direction, we studied this in forces, we always put a negative sign, if you remember with me. When we're calculating forces, when we're adding them, whatever it is, if you have forces and they go in opposite directions, we always include a negative sign. Now, the formula already had a negative sign, and that's originally in the formula, as you can see highlighted right here. Let me do it. This is a negative sign that already exists in the formula. Assuming that they're both going in the same direction, you still have to put negative. Now, because they are going in opposite direction, there was the original negative by the formula itself, and I added another formula because they're going in an opposite direction here. Because we have negative and negative next to each other, they turned out to be positive. So instead of negative, I had to put positive right here. Why? Because the formula already has a negative. Okay? And I added a negative because the ball and the bat are working in opposing directions. Negative and negative gave us positive. So yeah, and then after that it all becomes easy because the momentum at first was 3.8. The momentum at first was 3.2, and then it was hit with the bat, which is 3.8. Together they became this number, and you just need to divide it by the time given to you, and it gives you the value of 140 newtons. Now, what's the calculate the mean force exerted? Again, it says state the direction of the force. And it's talking about the bat. The bat, if you look at the diagram, it's clearly moving to the right. So the direction of it is the right. No issue at all. And state the magnitude and direction that the ball receives. The ball was moving to the left. So it hit the bat while going to the left with the exact same force. That should conclude it. By the way, this question, I think when I saw it on the mark scheme, okay, because it has 3 marks, people who solved it like this, F equals mv minus mu divided by t, and they took the final momentum as 3.8, and they took the initial momentum as 3.2, and they divided by the time, which is 0.005, and they didn't do the negative, the other negative, so it stayed as just one negative. They gave them 2 marks. And the people who actually added another negative, making it negative times negative gives you positive, and then solved it, they took the full 3 marks. Okay, so even an attempt without knowing this extra piece, which you should focus about, would still have gotten you the marks. Not full marks, but it would still get you some marks regarding such question. I had to make sure that all of the questions here were difficult ideas that we haven't faced before, so they're kind of like the toughest questions you might face of each question. All right, except for the moment one was not that deep. Like the only difficult thing about it was the first thing, the change, because of it having it in grams, but the rest of it is easy, you know. This whale question is difficult, but we faced it before, and the first question is an idea that is very unique. I've only seen once, but I solved it just to expand the knowledge that you have. You still have the other sheets attached, and you have the solutions to them, so I advise you start practicing the other questions that are simpler. Once you get a good hang of them, you come and practice these questions that we did right here. Thank you guys for watching, and ask me if there is anything that you need to know. Bye-bye.